So we'll do a little bit of review here as we kind of ease into section 5.1, which is going to talk about random variables, the probability distributions of random variables, expected values, those kind of things. So kind of good stuff, but let me just ask a random question of you to begin with. We'll do a little poll question. The state has a game called Club Keno. Now, Keno is a game that you play by selecting 20 numbers out of a set of 80 numbers. So let's see if we can't figure out, first of all, how many different ways there are that you can do that. What is the possibility? How many ways can you select 20 numbers from 80? Now, do you think that that selection process is going to be with or without replacement?
That sounds like without replacement.
Yeah, you're right. It's without replacement. So if you're selecting without replacement, and it's not going to matter the order that you matched, just what you matched, then it'd be 80, choose 20. And this could be a gargantuan number. Not sure what it is, but it's going to be pretty huge. Let me remind you on how to do that. I'll type in the 80 first, go to the math key, and then over to probability. Third one down is combinations. So there we go, 80, choose 20. There you go, 3.53 times 10 to the 18th. That's huge. So if we were to write that out, 353. Wow, let's see. Millions, billions, trillions, quadrillions. Wow, that's a lot of different possible winning numbers. So the number of choices that you have is going to depend on how many spots you play. You can play the 4 spot and select 4 numbers and try and match 4 numbers or as many as possible, and they'll pay you off accordingly. Or you can play the 5 spot, 6 spot, etc. I'm just curious to start with what spot that you would want to pick. So how many numbers would you want to pick and try and match? So I'm going to give you a little question in a poll just to see what you would say. And we'll take down the results. I've got that poll opened up, or at least starting to open up. And there you go. Let's see what we say. We'll look at this a little bit later. Right now, pick a number that you like because it's prime or because you wore it in New Jersey and playing your favorite sport or whatever. Let's just get a few more answers in here so we can compare it to what we've got later. All right, still about a quarter of you left to vote. Certainly we got a favorite here. My morning class kind of spread things out a little bit more. So there's no real right or wrong answer. Okay. Let me stop the results and I'll share them with you. So 14 of you want to play the 4 spot. And then 2 want to play the 5 spot. 3 want to play the 6 spot, 3 want to play the 7 spot, and 3 want to play the 8 spot. So other than a big group of you at the 4, still kind of spread out. So kind of interesting. Now, hopefully along the way today, we're going to learn some things that are going to help you make a better decision than just a random guess. And those things would be the expected value of a probability distribution. So let's go over a couple things. And I'll put this one in the chat once again, in case you're coming late. That is a handout for today. So got to make sure I send it to everybody, not just one student. So there's a handout for today. And it's going to start by discussing a random variable. So let's begin our work in section 5.1 here with a random variable. Random variable is something that has its value determined by chance. And most importantly, it has to have a numerical value that's determined by chance. So let's look at the first few examples down here. So this is going to be example A. And try and decide which one of these are random variables. And then we'll talk about random variables a little bit more in the form of a probability distribution. So let's see here. Determine whether the value is a discrete random variable, continuous random variable, or not a random variable. Now, what I highlighted here is that random variables have to be numerical values. And then if it is a numerical value that's determined by chance, is it discrete or continuous? You remember the difference between discrete and continuous? Discrete can only take in certain values. Continuous can take on any value in a range. So how about number A? The number of points scored during a basketball game. Is that a random variable? And if so, is it discrete or continuous? What do you think? Well, is the value there determined by chance?
No. There are a lot of factors to consider when scoring a basketball game.
Yeah, but those are, a lot of them are determined by chance, right? Does the referee call a penalty? Does your shot hit the rim and bounce out or bounce in? I mean, those all seem to like add up to a lot of chances. So I'd say there's a lot of luck in a basketball game. So we do have a numerical value. We can argue about its value being determined by chance, but is that value discrete or is it continuous?
Continuous. I'm sorry, discrete.
Discrete? Yeah, discrete because it can only take on certain values. That is, you know, integer values. You can't score half of a point. So this would be a discrete random variable. All right. Don, are you okay with that?
Yeah, makes sense.
Okay. All right. How about part B here? The time it takes to fly from city A to city B. So again, we'll assume that there is some randomness involved. You know, is there a headwind? How strong is it? Is there a lot of traffic getting into or out of the airport? You know, those kind of things. So it's going to be some value that could be anywhere in some kind of an interval. So does that make it a discrete random variable or a continuous random variable?
Continuous.
Yeah, that'd be a continuous random variable because it could be anything in some interval, as opposed to the number of points scored during a basketball game, which can only take on finite values. Let's move down to part C. And just to show you what I'm writing here, the first one was discrete. The second one was continuous. Let's look at the third one, which is eye color. Probability, excuse me, the eye color of people on a commercial aircraft flight.
Is it discrete?
All right, you got to vote for discrete. Does anyone want to say continuous or something else?
Continuous.
All right, got to vote for continuous. The last possibility, of course, is not a random variable. Anyone want to vote for that? And then we'll have a three-way split. No. Well, let me vote for that. Because the big thing in random variables is that they have to be numerical values. Is eye color a numerical value? No. No, it's not. So this one is not a random variable. It's just not. Case closed. It's not a number. So we don't have to think about it further. Let's look at part D here. the time it takes for a light bulb to burn out. I buy all these nice little LED bulbs that are supposed to last 10,000 hours. Gosh, they seem to burn out really quickly. I don't know what's going on. But in any case, the time that it takes for a light bulb to burn out.
Continuous.
What do you think? Continuous? Yeah. It's just like part B, right? Continuous random variable. It's a time. The number of statistics students now reading a book. Hopefully that's a big number, but it could be quite a lot of values. Those values form a discrete random variable or continuous random variable.
Discrete.
Discrete.
Discrete, right. You can't have 1 3/4 students reading a book. They have to be just nice, even integer numbers. So that would be a discrete random variable. And last but not least, back to basketball, the number of free throw attempts before the first shot is made. What do you think there? Can that be a continuous random variable? Can you have any numbers, numbers of any value? No, you're only going to get numbers in a certain range, right? You're not going to get just anything. Okay. Now let's talk about a probability distribution. Because a probability distribution is going to tell us what these probabilities are. It's going to say, okay, the chance of this happening is this. Now that probability distribution can be expressed in a couple ways. It can be in the form of a table, a formula, or a graph. So a lot of different ways, just as long as it conveys the probability of something happening, one of the values of a random variable. Now there's a couple restrictions on probability distributions. So probability distribution requirements. So what is it that's required of our probability distributions? There's two things, and maybe you saw one of them that was listed on our handout. The first is that all of your probabilities actually satisfy what we expect about probabilities. All of your probabilities are between 0 and 1. You can't have a probability outside of that range. And the second one, let me see if you guys can get this one. What's that saying?
The sum of all probabilities should equal 1.
Excellent. Thank you, Don. The sum of all the probabilities has to equal 1. Something's going to happen, and when you add up all the possibilities, that has to be 1. So, well done. Now, let me give you a link to a Google Sheets page, and what I want you to do when you get there is I want you to make your own copy. So let me find that page real quick here. And got to delete a couple answers here. Okay. So here's our Google Sheets page, and let me share that link with you. And I'll drop that one in the chat. It should open up, and you should be able to make your own copy. Somebody give me some feedback if that's working for you.
It's good.
Thank you, Sam. And thank you. All right. So my first question to you, and it's should be, let's see, is it in the handout? I hope so. Yeah, it's in the handout. And the question is this a probability distribution? So it's certainly a set of values of a random variable. X can be anything from 0 to 5 integer values. These are associated probabilities. But the question is, does it form a distribution? Well, there's a couple things we're going to look at. The first one is we're going to decide, are these values all between 0 and 1? And yeah, they're all between 0 and 1. But there was one other requirement that we had for our probability distribution, and that was it had to total up to 1. So does someone want to pull out a calculator for me? Oh, wait, there's a better solution, right? Let's hit the equals key and then start typing in the word sum. And it finally decides, oh, you want a sum. If you then hit the enter key, it should give you the sum and then a left parenthesis. Click and drag to highlight these cells. Now, if this is a probability distribution, what should that sum to?
1.
Should sum to 1. So your command should look just like this. We'll see if it sums to 1. And yeah, it does. And I can ignore the rest of this. I don't need it to autofill. So what we had there is a probability distribution. Nice. Let's look at example B now. Example B is something that you're going to face in your homework. And more I've done some of this, and that is I've put examples in the lecture of stuff that you're going to see in the homework. Now, what I want us to do is I want to look at these numbers first. And these numbers are in your Google Sheet if you want to look up at the top. We'll learn how to calculate these kind of numbers later on. But these talk about the number of boys or girls you can get when you're looking at so many pregnancies. So for instance, if you had 4 pregnancies, and you wanted to find out the probability of getting exactly 2 girls, that'd be 37.5%. If you double that, 8 pregnancies, 4 girls, now the chance of exactly 4 girls is 27%. Okay, still a pretty good chance. But then we keep on increasing these numbers. 20 girls, 40 or 20 pregnancies, 40 pregnancies, 100, etc. Now, if you had 100 pregnancies and you had exactly 50 girls, is that really unusual? No, it's kind of what you would expect, right? Or if you had 100 girls amongst 200 babies, still kind of what you expect. But what's happening to the probabilities as I keep on increasing the number of pregnancies that we're looking at?
The probability is decreasing.
Smaller.
Yeah, the probabilities are getting smaller and smaller. Do you remember at what point we classify something as a rare event? What's that breaking point?
5%.
Yeah, 5%. Perfect. And so even though it doesn't feel unusual that you get 150 girls out of 300 pregnancies, you know, it doesn't feel like it should be a rare event, and yet it is. Because what's happening is you keep on spreading out that probability amongst a wider and wider field of possible outcomes. So, yeah, there's just not as much room for any one particular event. Pretty soon, when this value then gets large enough, everything is going to be a rare event. And in this case, we've already reached it. Everything is going to be a rare event here. But it doesn't really feel rare or unusual to get 150 out of 300. So let's bring that back now to example B here. For 100 births, the probability of exactly 58 girls is 0.0223. And the probability of 58 or more girls, meaning 58, 59, 60, all the way up to 100, is 0.067. Is the 58 girls in 100 births a significantly high number of girls? Which probability is more relevant for answering that question? Consider the number of girls to be significantly high if the appropriate probability is less than 5%. So, well, typically speaking, what we do when we're looking at these kinds of probabilities is we don't just look at the probability of exactly this occurrence. We look at this or something more extreme. So what we would use here in this case is a probability of 58 or more girls. That's the more relevant probability. So I've kind of color coded it here in yellow to go along with this blank. The relevant probability is 58 or more girls. Now, if that's the relevant probability, is the probability of 58 girls in 100 births significantly high or not? So
No.
the second part.
No.
No, because that probability, we see it right here, is 0.067. And to be significant, it has to be less than 5%. So no, it's not unusual. So here would be a drop-down menu. You click it, it says is or is not significantly high number of girls because the relevant probability is not less than 5%. So that would be your answer. That's what you can expect here. Typically, I don't cover this early on in the course like this, but you will see something like this in the homework, and you're definitely going to see something like this later on where we start looking at the probability of this or something more extreme. So it's not a bad idea to introduce it here. Comments or thoughts on example B here? All right. Let's move to example C, rolling a couple dice. And I like this graphic. We've used it before for rolling a couple dice. And again, it gives us a chance to do kind of a little bit of a quickie review here. So this is example C. Example C. And rolling two dice is really the sequence of two events. Let's think about each of these. Now, assuming you have a six-sided die, there's 6 outcomes for the first one. And a twin of that die, 6 outcomes for the second one. That should give you a total of 6 times 6 is 36 possible outcomes. Now, how come I didn't use permutations or combinations or factorials here? It's because you can use these numbers again and again, right? You don't have to, it's not like you're sampling without replacement. So 6 for the first one, 6 for the second one. It's your multiplicative rule. Let's look at those probabilities. In particular, how many ways are there that I can roll a 4 out of those 36 probability or 36 possibilities?
3.
3. And you can see it here. I like how they've done this. They have different colors. 3 different ways you can roll a 4. 4 different ways you can roll a 5, etc. And so the probabilities then as fractions would be 3 out of 36, 4 out of 36 respectively. What roll is most likely with a pair of dice?
7.
7.
7, yeah. Because that's going to happen 1 out of 6 times. 1 out of 6 times, you're going to be rolling a 7. Okay. but we're going to go a little bit beyond that. Now, here's all this stuff as a decimal, etc. But what we want to do is we want to calculate something called the expected value. So let me talk about expected value and some of the calculations we're going to do next. Let's see. So we're going to do finding the mean of a probability distribution. Now, this is going to be different than finding the mean of a set of data. I'm going to use mu here, reflecting a population, equals the sum of x times p of x. That's how you're going to calculate the mean of a distribution. Now, it goes by a couple different names. For right now, I'll call it the mean. But in a little bit, I'll introduce a new term for that as well. Let's go to our Google Sheet. You should have a lot of that stuff here. Let's just take and delete a couple of these columns. So if you highlight the stuff starting in row 7 in columns E and F, let's just delete all of that so that we can practice calculating it ourselves. Highlight it, hit the delete key, should get rid of all those values there for us. I want to start with a clean slate. So here's your probability distribution for rolling a pair of dice. And you can see where I copied it into the handout. The two columns that I want to focus in on right now are labeled X and P of X. X is your random variable. P of X is its associated probability as a decimal. To calculate X times P of X, start by hitting the equals key. And then you want to click the two cells that we need to multiply, starting with A7. And then the times key is above the 8. So hit Shift 8. So A7 times, and now I want to click this cell underneath P of X. That should give me D7. So A7 times D7 should give you 0.0556. And I'm going to stop here because I want to make sure that everyone is on board with this calculation. I don't want you to get lost here. So I'll do this again one last time.
I'm sorry, but like, what are we calculating right now?
Eventually what we're going to calculate is something called the mean. And I'll give you a different term for that coming up, but we're going to try and find the mean of this distribution. So once again, you're going to start by hitting the equals sign, click the 2 that's underneath that X, a times or an asterisk, and then click the number underneath P of X, which is your probability of a 2, and hit enter. Now, the good news is that we don't have to do this by hand. I used to make people have to do this by hand. That's just not a whole lot of fun. Doing it on Google Sheets, what we can do is copy this down to the remaining cells. So grab the square lower right-hand corner and drag that down till it's even with the number 12 over there in column A. It should give you something like this. So this is all your X times P of X. According to this formula, to get the mean, I need to add all these things up. So we'll take and do that. And when you get that number, when you sum that column, then put it in the chat. Tell me what you get. Put it in the chat privately. Jalen, Kelly, Nicole, Reagan, Brandy, Noel, Mason, Brooklyn, Samuel, Ashley, all looking good. Leah, thank you. Katerina, Tia, nice. Oh, for that. Gonna have to look at that one. Okay. So you should be getting a 7. If you're not, let's see if we can't diagnose where the problem is. The first number I'm hoping that you matched was the 0.0556. How about the next number? Did you get 0.01667 and 0.333? Are you getting those
No,
numbers?
my next number was a 9.
Okay. Was the first one right? Did you get 0.055?
Yeah, the first one was right.
Okay. And you just dragged it?
Yeah, I just dragged it, and that's what I got. Can
did it
you
match the
click
rest?
on? Can you click on your second number and like what? It's AA and D8. Yeah, that's what I have. It's 3 times. Oh, okay. I know where the problem is. I figured
Okay.
it out.
All right, good. Good. So everyone should have a 7 then. Now, I'm going to give you a different name for this. It's called the mean, but it's also called the expected value. And you'll hear me use both of them. But right now, let me write down expected value. An expected value is nice because it gives you insight into what that actually means. What this is telling you is if you did this experiment hundreds and hundreds or thousands of times, on average, you would expect to get a 7. That's what you would expect. That would be your average roll would be a 7. Now, in this case, what's nice is that the number worked out so nice and even, and it's something we can relate to, rolling a pair of dice. That's all well and good. But one thing I want to point out to you is that if we were only rolling 1 die instead of 2, the expected value would be 3.5. And what's weird about 3.5 is you can't roll 3.5 with a single die. It just doesn't happen. Yet that's the expected value. That's what's going to happen on average. And so keep in mind that your expected value doesn't actually have to be a number in your probability distribution. Could be just sales. Could just be the average value. That's okay. We're going to want to pay attention to the expected value, especially when we go back and take a look at our Keno game that we started out things with. We'll see how you fare in Keno. All right. For now, let's move down to a different example. Example D. And do an expected value calculation here for the roulette wheel. Now, at least this isn't a modified roulette wheel, which is sometimes what you have to face in some of your problems at home. What's a regular roulette wheel? And what I would suggest to you is that you make yourself a little chart, kind of like the one that I'm going to make here. When you calculate expected values, you're going to want X for your probability distribution. You're going to want another column for P of X, and then a third column for X times P of X. So Okay, let's look at the problem here and understand a little bit about it. When playing roulette at a casino, a gambler is trying to decide whether to bet $10 on the number 35 or to bet $10 that the outcome is any one of 00, 0, or 1. The gambler knows that the expected value of a $10 bet for a single number is negative $1.06. For the $10 bet, the outcome is 00, 0, 1, or 0 or 1. You have a probability of probability of 3 over 38 of making a net profit of $30 and a 35 out of 38 chance of losing $10. So there we go. Those are the two values we had to work with. The values of our random variable. So we could either lose $10. Can someone tell me why I have the minus there?
Because you said lose.
Yeah, you're losing $10. Or you could win $30. Now the chances of losing $10 are going to happen 35 times out of 38. I hope you're not surprised if you lose. It's going to happen, mostly. Now, how about the probability of winning? Probability of winning is going to be 1 minus the probability of losing. So there's a 3 out of 38 chance that you're going to lose, or that you're going to win. And if you add that up, that would total to 38 out of 38, which conveniently is 1. That's just a double check on this kind of stuff here. To find the expected value, I need to take and multiply these together. So it's going to be this times this, and then this times this, add them all up. So let's see what happens when we do that. So I get negative 350 over 38, and then 90 over 38. Since I have the same denominator, I can add the numerators and get negative 260 over 38. That's my expected value. Awesome. Now there's something interesting about this number here. What's that negative reflect?
Money lost.
$6.80.
Yeah, you're losing. And this is known as the gambler's ruin. Eventually, if you play any of these games of chance at a casino long enough, you're gonna lose. The expected value is negative. It has to be, otherwise they wouldn't make any money. So yeah, count on this. Count on a negative expected value. With that though, which one of these would you choose? Would you choose this game, playing 3 numbers, or would you play a single number? Now, the expected value for the single number game was negative $1.06. I'll let you think about that and see if you get the right answer this way. I'm going to redo that poll that we did earlier, but I want to share with you some results here. And the results are the results from actually analyzing the game of Keno. So I did it for the 4 spot, 5 spot, 6 spot, and 7 spot. And here's the expected values for each of these. Now notice that they're wildly different, one from another, right? On the one hand, you have the 8 spot has an expected value of negative 0.25, 5 spot up here. So there's a lot of different values. Think about which game you would play. Let me relaunch that poll and see if the results change at all. I'm hoping that they do. Okay, need a few more in there. About 4 more. Almost there. 1 more, come on. There we go. Awesome. So let's take a look at that. Let me share the results. So this time we have a few more people doing the 4, only 1 doing the 5, 3 doing the 6. Still 3 want that 7 spot. 7 spot's not a bad play, and the 8 spot. Now, if you look at the expected values, if we look at the expected values, what I'd be looking for if I was choosing a game to play is the highest number. And that's the 4 spot. On average, you're losing about 9 cents out of every dollar playing that. The 7 spot's not too bad. You're losing 11 cents on a dollar on average. So that means if you played 1,000 times, you'd lose about $110. If you played the 4 spot 1,000 times, you'd lose about $92. But if you played the 5 spot, you'd be out a hefty $713. So the higher numbers, the higher negative numbers are kind of bad because that means you're losing more money per play on average. Now, can you win? Absolutely. If you couldn't win, people wouldn't play. But there's a big difference. In fact, I went through this, and if you want, I could share the link with you. You know, you've got your odds of winning are here in the 8 spot, almost 10 to 1. And up here in the 4 spot, they're less than 4 to 1. Man, I'd be playing the 4 spot all day. Look at the 5 spot. 5 spot really gouges you. 5 spot, you have a 90% chance of losing. I don't know why the odds are so stacked against you in the 5 spot. They're just really bad. It certainly pays to pay attention to some of these things if you're going to gamble. So, yeah, the house always wins. I mean, they literally should put up a sign, if you come to win, don't come in, because eventually they're going to win. But you know what? If you are going to gamble, then what you do is you bring money you can afford to lose. You play with it a little while. If you get up by a bit, you put some in your pocket, and then you play with house money. And if you lose that, you walk away a winner. But just know that you don't want to stay at the table too long. Eventually, the luck's going to change. And you see that in the form of a negative expected value. Now, there was somebody from Michigan that figured out a way that a certain lottery game would have a positive expected value. Jerry Selby, and him and his wife started recruiting friends, and they made $27 million legally betting on the lottery. He figured out that when the Michigan jackpots had a roll down, that there was actually a positive expected value to playing the game. And he started betting big during those times. And when they shut it down in Michigan, he found that they were doing the same thing, same roll down in New Jersey. There was actually a big stink about it because the State Lottery Commission became really curious as to why that there was some small little liquor store in the middle of nowhere that was selling $600,000 worth of lottery tickets. And they finally tracked this guy down and said, hey, what's going on? And he told them, hey, they're just playing the odds. And it was perfectly legal. He made $27 million for himself and his friends and his neighbors. And it was all legit. Doing the same kind of calculations we just did. So there you go. Math pays. In this case, it paid big time. All right, let's keep going with these kinds of problems. Let's do another one just like that. Again, this is coming straight out of your homework. It always does this one. I don't know why it does, but it just doesn't want to scroll for me. So we got a different lottery game. And if you want, we can do this one in Google Sheets as opposed to doing it by hand. Maybe that's good practice for us. But let's at least write down the relevant information for us. And the problem actually works you through it a little bit. In a state's pick 3 lottery game, you pay $1.29 to select a sequence of 3 digits from 0 to 9. If you select the same sequence of 3 digits that are drawn, you win and collect $462.42. Complete parts A through E. So the first question is, how many possible winning tickets are there? Well, to answer that, that's again one of our counting rules. There's 10 possibilities for the first one. And in this game, you're allowed to repeat the numbers. So there's 10 for the next one and 10 for the third one. So possible 1,000 combinations or 1,000 possible winning lottery tickets. So that's part A. If you're betting with 1 ticket to win, what are your chances of winning?
1 in 1,000.
Yeah, 1 in 1,000. 0.001. Thank you, Don. Now, if you win, they ask you what the net profit is. And you got to be a little bit careful here because the net profit is what you're going to use in calculating the expected value. So up here, I've got highlighted that when you win, you collect $462.42. But you spent the $1.29 to win that. So what's the difference? The difference is $461.13. Okay. Let's set up a little table like we just did, except this time we'll do it in Google Sheets. X, P of X, and X times P of X. There's 2 possibilities for our distribution. One of them is this. You could lose $1.29. The other possibility is you could win $461.13. Let's work on the probabilities here. Someone tell me what the probability of this random variable is. What's the chance?
1 in 1,000.
1 in 1,000. Thank you. So Don got the first one. Somebody tell me what the probability of losing is. If that's the probability of winning, what's the probability of losing?
999 over 1,000.
0.999. And we know that because this has to total up to exactly 1. Now, occasionally you'll see things that total up to something like 1.0001 or 0.999, something like that. More than likely, it's just a rounding error. It's actually meant to be a probability distribution. Now, if I give you a problem that I want you to decide if it's probability distribution, I'm not going to give you something that adds up to 1.001 and say, oh, no, you should have said no. I'm going to give you something that is far away from 1, far enough that you would realize it's not just a rounding error. Let's go back to Google Sheets here. Just find a blank spot. I'm going to put it down here for myself in column A, row 40. And I'll type in negative 1.29. And below that, I'll type in 461.13. So those are my X's. How about P of X? The associated probabilities of those variables. Well, this one is 0.999. This one was 0.001. And then I want x times p of x in that third column. And I'll pause here for a second so that you can catch up. Make sure you've got these typed into your little probability distribution correctly. And now in this column, I'll hit the equals key, click this, and then times. You can certainly find it with Shift 8. Maybe you've got a numeric keypad, in which case you can just hit it. Should be an asterisk, but you want the product of those two columns. Should be A40 times B40 or something similar. Now, when I do that, it asks me, oh, you want me to do that again for this one down below? Is it giving that for you as well?
Yeah.
So you should get a couple numbers like this. Now, by themselves, I don't necessarily really want those numbers, or it's not what I'm looking for. I want the total of those. So I'm going to sum up these two numbers. Yay. There you go. You should be getting negative 0.82758, etc. The important thing to notice about this expected value is that, like all your games of chance, your expectation is negative. You expect to lose. And in this case, you're losing about 83 cents on a dollar. So if you bet this game 100 times, you'd be out about $83 on average. That's what you would expect. I can repeat those calculations or anything you need, but how are you looking on these? Are you okay? Are you keeping up with that calculation? If not, this is the time to clean up such misgivings. You need me to show you certain formulas again, or are we okay there?
Could you redo it one more time? Just so
Sure.
I
Do you have all the values copied down first? You good there?
Yeah, no, I do have them.
Okay. All right. So I'm just going to highlight all these and delete them. So I'll start over from fresh. And I appreciate you speaking up. So starting out in the column next to my probabilities, I'm going to type in equals, because all my Google Sheets commands start with an equals. Then I'm going to click the first cell, which has my value of X. Now I need to hit an asterisk key. Now, if you got a keypad, you can just type the asterisk. If you don't, you have to hit Shift 8, but you want an asterisk. That means times.
Would equals product also work?
I don't know. It's a great question. I don't know. I do know that an asterisk would work. So equals product. Yeah, is that a Google Sheet command?
Yeah.
Check it out. Why don't you see if it works? And if it does, let me know. If it doesn't, let me know. It should. You should get.
I already did, and all the answers came out the same. I
Okay.
just didn't know if that would like work all the time.
I'll be honest, I've never used equals product, but my intuitive sense of it seems like it would work out okay. Ali,
Yes.
did you get these two numbers? Or did you get the first number?
Yeah, I was able to get both of them. Thank you.
Okay. And then we want to sum that up. So equals and then sum. And I'll just click those two and bam. So not the game that I'd be spending my hard-earned dollars on. No thanks. I'll make better decisions with that. I'll take my kids up north and go skiing. least I get a positive return on the investment there. All right. We looking okay with that first one? Or well, example D here.
Yes.
All right. I'm going to stop this recording here and we'll split this into 2 recordings.